Greetings. We are continuing with our lessons on photovoltaics, this being the last lesson by Dr. Nkateko E. Mabonza, who is a professional technologist in engineering registered with EXA. Our discussion today will be focused to energy conversions, where on completion we expect you to be able to describe energy conversions, use efficiency to transfer energy quantity from one format to another. We won't dwell on to energy saving schemes today, as that you already did. In a closed loop, energy will just be converted from one form to another. There is no new energy that's gonna come in. Let's take our planet Earth for instance. We look at an example where there is ocean water. The sun as a primary source of energy, heat the water there, and the water can be converted onto steam energy. So this was heat energy, and then this becomes steam energy, which goes and forms clouds. On clouds there, it becomes potential energy because it's at the height, and then it drops in a form of rain, and it fills up dams. And on filling up dams, it flows, now becomes kinetic energy, and this was kinetic as it falls. And this kinetic energy again drives a turbine, which is another form of kinetic energy, as it rotates motors and then create electrical energy. Then in your house, you're gonna use electrical energy to create other forms of energies. Charge batteries, you store it as chemical and so forth. But then there is no new energy coming in here. It's just a switch from one energy source to the other. So that's what energy conversion is all about in terms of closed loops. This leads to broader categories of energy, where we have stored energy, potential energy being it like in a height. You keep an object there, is stored. Whenever this is set free, it starts possessing kinetic energy, which is the second broader classification. Kinetic energy possessed by moving bodies, electrons, cars, you as human being, and so forth. As we transfer one energy to the other, we come up with losses. So, which means the energy that you feed in is not the energy that you get out. The energy that you get out is always less. Now, if you take the energy that you get out, I use P there for power, to the energy that you applied in, the ratio of the two, that will be efficiency. So input energy in a form of power into output energy will give you efficiency. So whether it's power, whether it's energy, it's the same. Remember, power is just the rate at which energy is given or at which energy is taken. Types of energy conversions. You can have chemical to electrical when you use battery. Batteries keep energy in a form of chemical energy, and you extract it, it becomes electrical, you power your devices. Then from electrical to other formats. It can be kinetic in terms of electric cars. And we have conversion of heat to electrical, steam turbines that rotates and give electricity. We've got one more interesting, light energy to electrical, a photovoltaic, a light which that shines in a photocell, and it creates an electrical signal where you're gonna have certain current and certain voltage. That was discussed, is a revision. Moving to efficiency, and we have a closer look. Here they even indicated in power, so it's more of a habit to not to use E but to use power. So that is expressed in percent as a ratio of an input to output. So you've got some form of power or energy fed onto the system, it becomes an output. If you take the ratio of the two, that's how you get efficiency. But now imagine a system where a network where you've got more than one unit. So the total efficiency, if this is efficiency 1, and that's efficiency 2, and efficiency 3. If you multiply all the efficiencies together, you're gonna get a total efficiency. So that's how you get an aggregate efficiency for various systems that are interconnected. Other than efficiency, we've got constant that aid us to transform one figure to the other. For instance, if you've got a circle and a radius r, to translate it into area, you're going to use a constant pi, which you multiply by the radius squared. We have things like c, which is used when you calculate the wavelength with a given frequency. So where wavelength lambda is equals to c over f. So that's another constant. We have gravitational acceleration, that is used when you translate you get energy from the mass of an object and the height. Let's get an example here. In a photovoltaic system where you use that to boil 25 liters of water. So the question here is, how much power must your solar panels give for you to heat up 25 liters of water when you use a 230 volt supply, right? So here we are given a typical efficiency values for specific heat capacity. That is the constant that you use for water when you convert liters to the amount of energy required. So it's 4,200 joules for every kilogram and degree Celsius. But where 1 joule, remember we work in watt hours, is equals to 277,7 or 277,778 microwatt per hour. We're not clear there if this is comma or joule 277, we'll see it as we go along, 778 microwatt per hour, and 1 liter is 1 kilogram of water. So the other efficiencies, we've got cables 97, inverter 92, battery 97, heating elements 79. Those are typical values. If you buy those devices, you can check in the manual. Now, energy in joules is change in temperature, mass, specific heat capacity. Right. Okay, now we put that formula onto action. Right. So that is actually 277,778 microwatt per an hour. Right, so it's not 1,000, it's a comma. So it's 277, comma. So you multiply that together, and your total energy in watt hours is 2,187. So that there was supposed to be a dot, watt hour. Now the total efficiency, remember I said if you've got several efficiencies interconnected, you multiply. So they multiply that cables, inverter, charge controller, whatever was listed there, it became 0.663. Now, because you know that P out over P in is giving you efficiency. So if you take efficiency, you multiply by, you divide it onto P out, you're going to get P in. So from that formula, we just make Pi the subject of the formula, and that will give you that is the power. But now it's the energy rather, sorry. The problem here, we're using P to represent energy. Now it becomes difficult to differentiate which one is power, which one is energy. The proper way would have been to make this energy EI. So now we switch to get to power. Now that value C is a result of you multiplying power with time you have. So as a result, you will be able throughout the whole day, you effectively you have 4.5 hours, which was given as peak sun hours. So you divide and then you get this amount of power. Bear in mind that this heating by this solar panel of 732,825, it will take the whole day to boil the water. Right. It's gonna take, so if you wanna make half a day, you might have to double the solar panel and so forth. But that's what you need to boil water throughout the day, with an assumption that it's a clear sky day, which gives you 4.5 hours as a peak sun hour. Then the other thing here is how to look on converting mechanical energy onto chemical. So you're using a battery to move a boom gate to a height, and there are a loss of friction which is given there. You're moving it by 2 meters. Elevation is 60 degrees. And you move it 100 times per day. It works for 31 days. Well, you need an amp hour of a 12-volt battery, but you've got opposing force of 5%. So that is an opposite of efficiency. If you say the opposing is 5%, then it's a tricky one. Now it means efficiency there is 1 minus 0.05. then it's 95%. That is your efficiency. Now, the energy which we can know is this one, but the actual energy which is used is that. Right, so we can calculate that using MGH formula, mass times gravity times height. Let's see how they do that. The vertical energy is that, so they've calculated it. There's 2 meter, there's 9,8 constant. There is another figure, 3. What was 3 again? Let's check there. Okay, maybe we can look at that, because we have got G is a mass, 3 kilogram. Now that gives you 67,896 joules. But then we have to convert it onto watt hours. We know that 1 joule is equals to 2,778 microwatt hour. So they've changed joules to that, and then the joule was supposed to be disappearing there, because now you substitute with 277,78, and then it moving how many times? 100 times for 31 days, and you divide by the efficiency of 95%, and then that's the energy which you use. Remember, the energy that is going like this, that is the resulting energy, because the boom gate move like that. That's why you're dividing by sine of that angle. You're translating what you know, the height MGH, to what is unknown, which is that. Right, then having the energy of 5.466, you see the unit is in watt hour, but watt hour is VI. So if you want to cancel V and remain with M hour, you have to divide by voltage. Again, don't forget that battery has got, you can remove 60% of it. So you're gonna remain with 1 minus 0.6. That is there. And the efficiency was already considered there. Okay, so overall, the battery which is required is equals to 16,8. So this is 80%, which was the total efficiency there of the motor there. Right. So you consider the efficiency of the motor and the depth of discharge, and then you have 16,026 hour. That is a good example. Just study that, make sure you understand. Actually, the values, you might find that they are not precise, because there are assumptions about the frictions and so forth. That brings us to the conclusion of our lesson on photovoltaic. Go through your notes to cross-check whatever we discussed here. Anything that you don't understand, make an effort to contact your instructor. Good luck with your career in photovoltaic energy. Cheers.